Let's start with a strange idea. Modern CPUs regularly execute instructions that will never actually happen. Instructions that will never commit. Instructions that will never update registers. Instructions that will never change memory. From the perspective of the final program result, these instructions simply never existed. Yeah. And yet, the CPU fetches them, decodes them, schedules them, executes them. Millions of times per second.
Why?
Why would a processor spend energy executing instructions that will eventually be thrown away? The answer lies in one of the most important techniques in modern processor design, speculative execution. And once you understand speculative execution, you begin to understand how modern CPUs reach the incredible performance levels we see today. Because without speculation, modern processors would be dramatically slower. The core problem, waiting is expensive. At the heart of the problem is a simple reality. CPUs hate waiting. Waiting wastes cycles. Waiting wastes hardware resources. Waiting wastes performance. Modern processors are designed to keep as many execution units busy as possible, but programs constantly introduce situations where the CPU doesn't know what to do next. The most common example is branching. Consider a simple piece of code.
Forget our spatial extension, so I'm just doing that, please. Do A, else
do B. When the CPU reaches this branch instruction, it must decide, do execute, do A, or do B. The problem is that the CPU cannot know the answer immediately. It must first evaluate the condition, and that may require waiting for a register value, a memory load,
a previous computation,
which could take several cycles. If the CPU simply waited until the condition was known, the entire pipeline would stall, and pipeline stalls destroy performance. So instead of waiting, the CPU makes a guess. Branch prediction. Modern CPUs include sophisticated hardware called the branch predictor. Its job is to predict which direction a branch will take before the answer is actually known. For example, will the branch go to the if path or the else path? The predictor uses past execution history to make this decision. If a branch usually goes one direction, the predictor assumes it will go that way again. And most of the time this works. Real programs often behave predictably. Loops repeat.
conditions behave consistently.
So predictions are frequently correct. But here's the key idea. Once the CPU predicts a branch direction, it does not wait. It immediately begins executing instructions after that predicted path, even though the branch condition hasn't been resolved yet. This is the moment where the CPU begins executing instructions that may never happen. Speculative execution begin. When a branch prediction is made, the CPU starts executing instructions speculatively. This means the CPU acts as if the prediction is correct. It fetches instructions from the predicted path. It decodes them, it schedules them, it executes them, all before the branch condition has been confirmed. These instructions are called speculative instructions. They are temporary. They exist only under the assumption that the prediction is correct. If the prediction turns out to be right, everything continues normally. But if the prediction is wrong, everything must be undone. Why speculation is worth it? At first glance, this seems wasteful. Why execute instructions that might be thrown away? Because the alternative is far worse. Without speculation, the CPU would need to pause every time it encounters a branch. And modern programs contain branches constantly, roughly every 5 to 7 instructions. Without prediction and speculation, the CPU pipeline would stall continuously. Instead of executing multiple instructions per cycle, the processor might drop to a tiny fraction of its potential throughput. Speculation keeps the machine moving forward, even when the future is uncertain. Out-of-order execution makes this possible. Speculative execution works because modern CPUs are out-of-order machines. Instead of executing instructions strictly in program order, the CPU allows instructions to execute as soon as their inputs are ready. Inside the processor, instructions are stored in structures like the instruction window, reservation stations,
the reorder buffer.
These structures track which instructions are ready to execute. And importantly, they also track whether instructions are speculative. Every instruction carries a dependency chain back to the branch that enabled it. So the processor knows exactly which instructions belong to which speculative path. This bookkeeping is critical, because if a prediction turns out to be wrong, the CPU must remove every instruction that depended on it. The moment of truth, branch resolution, mesport Califeld Tan, Afghanistan te bouw pluis hier punsing diamortum fingers stotem, and as on narcotics control board of the Biesen intuited, the treater, the tingse, de village to patchen too. See mo the gishen, toin de latitak tots upon stations, to the panst, by dear de person the paleth bala. Eventually, the CPU computes the actual branch condition. This is called branch resolution. At that moment, the processor compares two things: what the branch predictor guessed and what the program actually required. If the prediction was correct, nothing special happens. The speculative instructions become real. They simply continue toward retirement. But if the prediction was wrong, a dramatic event occurs. Pipeline flush. When a branch misprediction happens, the CPU must discard everything that came after the incorrect prediction. This includes instructions waiting in the issue queue, instructions executing in functional units, instructions waiting in the reorder buffer. All speculative work based on the wrong path must be removed. This process is called a pipeline flush. The CPU clears the speculative instructions and restarts fetching from the correct branch path. All the work done on the incorrect path disappears. From the perspective of the final program state, those instructions never existed. They were executed, but they never happened. Architectural state versus speculative state. The reason this works safely is because speculative instructions cannot update architectural state immediately. Architectural state includes
Architectural registers.
Program visible machine state.
Instead, speculative results are stored temporarily in physical registers and internal buffers. Nothing becomes permanent until instructions retire. Retirement is the moment when the CPU commits results in program order.
Only retired instructions are allowed to update architectural state.
If a branch misprediction occurs before retirement, the speculative instructions are simply removed. Their results are ignored, and the architectural state remains correct. The reorder buffer's role, the structure responsible for enforcing correct program order, is the reorder buffer, often called the ROB. When instructions enter the out-of-order engine, they are placed into the ROB. The ROB tracks
instruction completion,
receptions, exception, speculation status, retirement order. Even though instructions execute out of order, they retire in order. This ensures the machine behaves exactly as if the program executed sequentially.
When speculative instructions finish execution, they wait in the ROB.
if the speculation was correct, they retire normally.
If the speculation was wrong, the ROB discards them. No architectural state is affected. Speculation happens everywhere. Branch prediction is the most famous source of speculative execution, but it's not the only one. Modern CPUs speculate in several ways. They speculate on branch direction, branch targets, memory dependency, load ordering. For example, CPUs often speculate that loads are independent of earlier stores. If the guess is wrong, the load is replayed. Speculation is everywhere in modern processors. It is one of the fundamental strategies used to keep hardware busy. How often does this happen? In real workloads, speculation happens constantly. Branch predictors may achieve 95–99% accuracy, which sounds extremely high. But remember how often branches occur. Even a 1% misprediction rate means mispredictions happen regularly. Every misprediction triggers a pipeline flush. Every flush discards speculative work. So modern CPUs are continuously executing instructions that will never retire. And yet the performance gains are enormous. Because the correct predictions vastly outweigh the incorrect ones. The cost of a misprediction, branch mispredictions are expensive. When a misprediction occurs, the CPU must flush speculative instructions, restart instruction fetch, refill the pipeline. This process can cost 10 to 20 cycles on many processors. On very deep pipelines, it can be even more, which is why enormous engineering effort goes into building extremely accurate branch predictors. Because every improvement in prediction accuracy directly improves CPU performance. Why programs still appear sequential? From the outside, programs appear to execute exactly as written. Instruction by instruction, line by line. But internally, the CPU behaves very differently. Instructions execute out of order. Speculative instructions run ahead of the program. Incorrect work is thrown away. Yet the architectural illusion remains perfect. The reorder buffer and retirement logic ensure that the final visible behavior matches the program's original order. The complexity is hidden entirely inside the processor. A strange consequence. This leads to a strange philosophical observation about modern computing.
The CPU often explores multiple possible futures of a program.
It guesses what will happen, executes instructions based on that guess, then later determines whether that future was real. Most of the time, the guess was correct. But sometimes the CPU briefly lived in the wrong future, executed instructions from it, then erased that reality completely. Speculation and security. Speculative execution became widely known outside processor engineering after the discovery of attacks like Spectre. Meltdown. These attacks exploit the fact that speculative instructions can still affect microarchitectural state, even though they never retire. For example, speculative instructions may change
cache contents.
timing behavior. Attackers can measure those changes to infer sensitive data. This revealed that speculative execution, while invisible architecturally, still leaves traces in the hardware, and those traces can sometimes be observed. This discovery triggered major changes in both CPU design and operating system security practices, the invisible work of the CPU. So the next time you run a program on your computer, remember something remarkable. Inside the processor, millions of instructions are being predicted, millions are being executed speculatively, and many of them are being thrown away. The CPU constantly explores possible futures of your program, trying to stay one step ahead. All so that when the correct path becomes known, the answer is already waiting. That is the secret behind modern CPU performance. And it is why processors regularly execute instructions that never actually happen,